Bismillahirrahmanirrahim. Auzubillahi minash-shaytanir-rajim. Bismillahirrahmanirrahim. And now I will start the part 2 of this lecture, which is about how we do the same thing in the Bayesian world. But that will take some time to develop, and I'm just going to start the basics today. So in the Bayesian model, we start by, you see this P, that is the unknown thing that we are trying to find out. It is a fixed and unknown number. But the Bayesian calculation begins by assigning it some probability distribution. So what is this probability? Then this has been always the source of the rejection of Bayes. The conventional probability theorists reject the Bayesian inference because they say that you have a fixed number P and you are assigning it a probability. Of course, they do the same trick when they do the confidence intervals. They actually treat the P, so there's no choice about that, but it's just the question of how you do it. So the Bayesians say that, okay, I'm going to assign a prior distribution to the unknown parameter, and we will discuss what this is and what it means. But basically, the meaning of this prior distribution, and this is where the confusion arises, is that this is a fixed number. The distribution is now a state of my mental uncertainty about P. It is not really a reflection of what is happening in the real world. So what we do, there are very many ways to describe my uncertainty. I can say that, okay, P, I think it will be between, how many modes will be? I think it will be between 30% and 4%. Okay, so this is my knowledge about P. But I want, in the Bayesian calculation, I want more than that. I want to have a full probability distribution. That is called the prior distribution. And as I've said, there is an argument the Bayesians use to prove that you have a prior distribution. But that argument is wrong. But it doesn't matter. We can still say, let's pretend that I have knowledge of P, which is described by a distribution function. So my lack of knowledge about P is represented by this prior distribution, which shows the possible values of P and gives them probabilities. So okay, so if I say that I think P will be, I think P is 50%, and in my mind the probability of that is 25%. I think it is 60%, and that is also in my mind. So there are 4 equally likely possibilities. It's 50 or 60 or 70 or 80, and all of these in my mind are equally likely. So that's a prior distribution. A prior distribution specifies certain possible values of P and gives the probabilities for that. So it's just like a random variable. Now, because P is a continuous variable, it doesn't get a discrete distribution, it gets a continuous distribution. And a continuous distribution is called a density, f of P, which satisfies 2 conditions. It has to integrate to 1, because the integral of the density function gives you the probabilities, and it has to be greater than or equal to 0, because probabilities are non-negative. So these 2 conditions, any function satisfying these 2 conditions is a prior distribution for the parameter P. So now, practical problem for Bayesian theory is that nobody knows enough about P to be able to specify a prior distribution, because a prior distribution requires a lot of information which we don't have. So what is done? The solution is very simple. We pick, just like you pick a sample of convenience, so we pick a prior of convenience. A prior of convenience is one for which you can do the calculations. So this is called the natural conjugate prior. In most problems, there's a prior density which is called natural conjugate. Natural conjugate prior has a form which matches the data density. So the binomial has a certain shape and the prior distribution has a certain shape. These two match. When these two match, then the calculations become very easy. So it turns out that for the binomial density, this is called the beta density, which is defined as gamma of beta 1 plus beta 2, gamma of beta over. So now what happens is that when people who are non-mathematicians look at this, then they faint. And they say that, okay, this course is not for me. This is, now we have seen the gamma distribution. I am so scared. So this is nothing. I mean, basically the gamma distribution is there to scare you. So don't worry about it. The thing is that it's the real thing. That's just a constant. In Bayesian calculations, all the time we get huge, monstrous coefficients, constants, which scare even me. But you just ignore them, because it turns out that the constants don't matter in these calculations. What matters is actually there is a name for this. The kernel of the density is the part which involves theta. So the kernel of this density is theta to the beta 1 minus 1 times 1 minus theta to the beta 2 minus 1. The other part doesn't matter, the constant, because it's just something which makes this integrate to 1. And we can always find it out numerically. But the kernel is important, because the kernel is, you can see, matched to the binomial distribution, which has p to the something and 1 minus p to the something. So here's theta to the something and 1 minus theta to the something. This is beta 1, beta 2. Also we use alpha and beta for the beta distribution. Now, what we need to do is to understand density functions. What is a density function? What does it represent? And the process by which you generate a random sample from this density, and the reverse. Given a random sample, how do you learn what density it came from? So this is crucial. This question is at the heart of all of probability and statistics. You have a theoretical distribution, which is the population. You draw a sample from it. If you know the population, what will the sample look like? All of probability theory is about this question. All of statistics is about the reverse question. You have a population you don't know, you draw a sample. Now from the sample, what can you learn about the population? So these probability and statistics are opposite halves of the same question. The relation between the density and the random sample from that density. So now I'm going to examine this question in the very special case of the beta density. As I've explained to you, the principle of learning that we learn in the beta, we learned it in normal, we learned in Poisson, and then we will see the big pattern of what is going on. So you have to keep both things in mind. We are working here with the special beta density, but also we are working with the general principle of how does a sample relate to the density which comes from. Okay, so now there are some pictures. I'll go to Excel where we will start seeing this much sooner. Okay, so if you have beta 1, 1, that is a uniform density. Let's look at this. So 1, 1 means that beta 1 is 1 and beta 2 is 1. So 1 minus 1 is 0 and 1 minus 1 is again 0. So basically theta disappears. Theta to the 0 is 1. So if the density is constant, then it has to be 1, because that's the only density which integrates to 1. So the gammas again disappear, and so basically this is the uniform density. It's equal value of 1 for all points between 0 and 1. Remember, the beta density is only between 0 and 1. It's not outside, because it's a density for the probability p, and the p can only take value between 0 and 1. The second case is that if you have 1 and 2, that's triangular density. Again, you can see this. If you have beta 1 equals 1, theta 1 disappears. Theta 1 to 0 is 1. And beta 2 equals 2, then beta 2 minus 1, 2 minus 1 is 1. So you have just 1 minus theta. It's a linear function. And that's the graph of the 1 minus theta. If I made it 2 and 1, then it will be theta. It will be a line going up. And here are some other densities. So here 2, 1, this is the red line, is the 2, 1 density. And now as I increase to 4, 2, 6, 3, I am just adding, going up in integer sequence 1, 2, 3, 4 and 2, 4, 6, 8, this density starts becoming concentrated. It becomes more and more fixed and up towards one value. And this is now we fix one of the parameters 2 and start increasing 1, then it becomes skewed density, and it starts moving towards the right, and ultimately it will become very close to 1. These are, if you just keep increasing the numbers 1, 1, 2, 2, 3, 3, 4, 4, then it remains symmetric and it starts concentrating near the center, 0.5. And now if you start using numbers below 1, then the density acquires a very, because now you have a negative power of beta 1 and beta 2. So these things go to beta, as you have 1 over beta, near 0 it starts going off to infinity, and 1 minus beta near 1 it starts going out to infinity. So it goes off to infinity near both ends as you use numbers below 1. So it becomes a reverse, it's a cup-shaped function. So the basic thing is that the beta densities represent a very large number of different types of prior information that you can have. So it gives you a fairly flexible prior, but there are some kinds of things that beta cannot do. If you have a bimodal density, beta cannot be that. So sometimes you have information that either the probability is 25% or 75%. This kind of prior information cannot be represented by a beta density. So now I would like to show specifically how I will show all of these things actually. What the densities are and what do random variables look like, and how do we generate random variables from densities. So here I have alpha 1 and beta 1, and I have put down x. X is my, let me maximize this. X is my ordinates, 0, 0. Now what I have done is I have replaced 0, 0 by 0, 0, 1, because some of the, especially you see when you have the negative numbers 1 over theta, it becomes infinite and causes problems. So I don't need the value exactly at 0 and exactly at 1. I start with 0, 0, 1. Then I just take 1/20th, 0, 5, 1, 0, 1, 5, 2, 0. So I'm just trying to make a graph of the density. So these are the x values at which I'm going to be graphing. Then I have this. Excel has a built-in function, beta.dist, and I am putting in the first argument is x. The second argument is the first, which is alpha minus 1. So alpha here is 1, remember? So the theta is going to cancel out. Then I have beta equals 2. So the 1 minus theta is going to receive a 1 power. And then the false just says that I want the probabilities, not the cumulative distribution function. Later on I'll use the cumulative. So at this point it just gives me the graph. As you go down, I have just the beta of x. It just all of the parameters are the same except for the the x value keeps changing, a, b, and the same. So this is the graph of the function with beta equals 2. Now let me just show that. Okay, I'm going to change this to 2. Oof. Dell campus, man. Okay, so this is 2. Now what will happen? What will happen? The graph will change. What will it change to? Oops, that's not good. 2.
So beta is also 2.
Oh, I see. This is theta times 1 minus theta. It's a quadratic function, right? It's theta times 1 minus theta. So it's a quadratic function, and it's a perfectly centered quadratic on 0. I thought I was going to generate the uniform, but that's not the uniform. How will I generate the uniform? If I put 1, 1, it will generate the uniform. Okay, so this is the uniform. And if I want to generate, the other triangle, the other line, it's 2. Oops. Oh, ये तो पहले ही था. अच्छा. 2, 1 will generate the other line. Beta equals 1. Okay. So these are the lines, and we can get more complicated stuff. If I change this here to 5, and okay, so 5 and 1, it's just theta to the 4th power. So this is so there are many different types of densities which can come out of the beta density, and all of these represent my belief about theta. Now what we are going to do is to discuss the second part, that okay, this is the density. What do the random variables look like that come out of this density? And those random variables represent actually more clearly to us the state of our knowledge. So now the easiest way to generate a random variable from a density is by discretization. Instead of taking the whole range, I am going to just consider breaking it up into a 10th part. This is a coarse discretization. I can break it up into 100 parts or 1,000 parts, and they all work the same. So I'm going to break it up into 10 parts. So I'm going to take the interval from 0 to 10, from 10 to 20, I mean 10% to 20%, and all of these. And I've already done that. I've set it up so that we can do that. Now, the number that is of interest to me, for each interval, there actually now we have 11 intervals, right? One going from 0 to 1, and then 1 to 2, and so on up to 9 to 10. So I think we have 11 intervals or 10 intervals. Anyway, it doesn't matter. What I want to do is to take the midpoint of that interval as the representative. That instead, when a random variable takes values between 0% and 10%, I will call this 5%. So this is called discretization. I'm making an approximation. My approximation will be valid within plus or minus 5%, because I'm making a very big grid. Just to understand, I can if I make a grid of 100 points, then my approximation will be valid to within 0.5% accuracy. And if I make it 1,000 points, then it will be valid to within 0.005. So I can make it as accurate as I like. But the principle is the thing to understand. Now, how much probability should I put at 0.5? How's that? You are suggesting the trapezoidal rule, that we take the density at the two endpoints, and we take the trapezoid that is formed, and we take the area. That is a good approximation, but we have a better possibility here because Excel has given us the integrals. So what I do is, this is the value of the CDF at 1, 0, and this is the value at 0. So this is how much probability we have at 10%, and this is how much probability we have at 0%. If I just subtract, this will give me the probability in that interval. So that's what I have done here. You see, this is C6 minus C4. So that's the 0.000432 minus the probability of 0, which is actually 0. So basically you have the probability in the first interval, that's assigned to 0.5. Okay, the next number, 0.10, that's C7 minus C5. So this is 15% minus 5%. That's the probability at this. But I don't want the 10%. because I'm going to take 5% and 15%. So this is the value at 15%. Value at 25% is the value between C10 minus C8. It's between 30% and 20%. And now I make this table over here of values. Okay, so the table is 0, 5. The probability here is 19%. How did I get this? Oh, I see. Oh, this is some other alpha beta that I was working with. So that's why I have this. So I can actually replicate this distribution. I don't remember what alpha beta I was using.
1, 2, sorry.
1, 2 triangle. Okay. I think it was the triangle. Exactly. It was the triangle I was working with. Okay. Let's work with the triangle. So triangle is 1, 2, right? Yes, exactly. 1. ठीक है इसमें 2 डालते हैं. Okay. So now I have 19% over 18.8%. It turns out that this is because I have made some distortion near 0. So it's actually 19%, which is what I have. Then at 115 I have 17%. And so I basically copied those numbers. So it goes down in linearly, 19, 17, 15, 13, 11, 9, 7, 5, 3, 1. It's perfectly linear. It is a linear function, right? So that's my, and these numbers add to 1. That's very important. So now what I'm going to do is I'm going to, so now the beta density is the density in which I have these 1, 2, 3, 10 outcomes. Okay, I have 10 outcomes. One is 5%, 15%, 25%, 35%, 45, 55, 65, 75, 85, and 95. So this is the thing that you have to understand the nitty-gritty detail down to the ground if you want to understand general theory. And both of these things are simultaneously important. So I'm giving you the exact numbers. So now I have these 10. Now what? And so basically the beta density with 2, can be understood as a density in which we have these 10 possible outcomes with these 10 possible probabilities. Okay, this is accurate to within 5%. This is an approximation to the beta density which is accurate to within 5%. Now, what I want to do is I want to generate a random variable with this probability. So for that I need to do data, and let's see what happens. So here there is data analysis, which is what we will use. If you do it on your own, you might not find data analysis because this has to be installed from the add-in. Does everybody know how to do that? Yes. Okay, so then I don't need to show how to do that. So we go into data analysis and we want to do random number generation. Wow, who has been working on this? I have not been working on this laptop, but it is set up for. Okay, so now I'm going to just set the number of variables to be 1, and I'm going to generate 100 random variables. And now I'm going to use this value probability and input range. I want to move this if I can. Yeah. Okay. So now these are the outcomes, and those are the probabilities. So Excel allows you to give it a table, and in this table I have outcomes on the left in the first column, and the probability of each outcome in the next column. So now it's going to generate my, okay, so that's, and now I'm going to put the output range. I just want, instead of a new ply, I want to see output on this, and I'm going to just put it at O1, which is what I have. O1. O1 is the 0th column, and I'm going to look at the outputs in that column, and I'm going to say OK. क्या हुआ? हाँ, discrete है ना. This takes on these 10 values. That's what its discrete distribution is. Okay. So I'm going to overwrite existing data. Okay. Acha. Right. So it knew I was going to do that because the sheet was from there. So here is the first random number generated was 0.25. The second one was 0.5. Third one was 35. So this is a random sample which is coming from the beta density, from an approximation to the beta density. Now, what I want to do, okay, so these are 100 numbers which are coming out from the beta density. Now I want to analyze these 100 numbers to see what they look like and to match them to the beta density. So first I select a bin range. I'm going to make a histogram of this. So I select a bin range which is 0, 0.1, 2, 3, 4, 5. So each bin has only one number in it this time because of the way we have set it up. So now I'm going to go into data analysis again. And let me move this so that we can come over to this side. हाँ, इसके ऊपर चार्ट पे चले जाए. इतना बेवकूफ है ये एक्सेल. ये आ गया. Okay. So now we do data analysis, and now I want to do a histogram. And I say okay. And now the input range is going to be O1 to O100. That's my random numbers. The bin range is going to be, I have to specify it because I cannot see it. Acha, P3, huh?
P3 to P13.
P3 to P13, right. Okay, so that's my bin range. And output range is going to be Q1, okay? Yeah, Q2. Yeah, I will overwrite the data. Okay, go ahead. All right, so now I have 23 observations in 0.1, which means that 0.05 occurred 23 times. And then I have 19 observations in the second, so the 1.15 occurred 19 times. Now these numbers should be compared to the probabilities which are over here. Oh, see, they are. I have plotted them there. 23 has come out to 0.23. That's the 23% probability. So 19% over here, 12% over there, and so on. So what we have here is the observed frequency. This is the pre-experimental number, 19%. That's the probability of all possible outcomes. The 23% is the post-experimental number. This is what actually happened when we did the random sampling. And you can see that there is a rough match between them. And actually the chart shows what's going on. I have made this chart from these numbers. So the blue line is the theoretical probability. It starts at 19%, and the orange line is the match of the observations. And you can see that the observations are roughly matched to the probability. So this is basically what we do. The random sample resembles the beta density roughly to this extent that if you draw the density from the observed frequencies of the histogram, then the orange line matches roughly to the blue line. Now one more I'll do this one more time just so that we can see how it goes. Histogram, okay. Okay, we just repeat it. We overwrite it. See, the first time you do it, it apparently comes out the same. What? Okay, so what I'm going to do, 23, 19, 12, 9, 11. Is it the same or different? Acha. Okay, so I wanted to generate a different random sample. So there is a way to do that. कहाँ पे है seed इसकी?
उसमें random numbers में seed.
ओ अच्छा हमारे जो वो O1 का to O100 है वो तो same है, इसलिए we are getting the same things. Okay, I can generate a new set of sample and it will generate the same kind of graph. All right, so now let's see, what do I want to do here? Yeah, right. Now the interesting thing is that we can make this more refined, and yeah, if you want, I can take another sample by go to random number generation. I think everything is okay. We can just keep it like this. Allow it to overwrite. Okay. Now it has generated a new sample, and now I have to go again to the histogram because it's not dynamic. And now I think if I do it, overwrite. Okay, now we have a different graph, but again it's closely matched, and no matter how many times we do this, we will get a roughly similar graph, but the discrepancies can be very large. So this is the probability that 95 times out of 100 you will get a close match, but 5 times you might get a very wild looking graph. You might get something which is an orange line which is going in the opposite direction. So this is the problem, that you can never be 100% sure. You can sometimes get very large deviations. So basically we can say that orange line and blue line will be close to each other with 95% probability, and we can put a bound on how far they can be, but even that bound is a 95% confidence bound. If I run this experiment 100 times, then my bound will be violated 5 times, and 95% of the time it will not be. So basically we have established the issue of how to match. Now we can do further, and you should do this further, in the sense that make the divisions up to 100 and then do the same experiment. That way you will learn how to generate random variables. One of my students recently is working on MPhil for a long time, and he had to generate random variables. So there are many other methods for generating random variables. In fact, my brother Arif Zaman at LUMS, he is famous for an algorithm, if you can find his name in Wikipedia, for generating random variables. But all of those methods are very complicated. This discretization method is the simplest method for generating random variables. It requires no real. But of course, that's not really the solved problem that was solved by the random number generators, because I'm using the built-in Excel tool, which basically bypasses the whole problem. So as long as Excel is giving me a way to generate discrete random variables, I'm just following it by discretizing and calculating the probabilities from the CDF. If you go through this, you will understand. So this is one part of the process. And of course, you can understand that this will work for any density. It's not just the beta density. So although I have demonstrated for a very special, real, concrete case of a triangle, you can do it for any other beta density that you like. And it doesn't have to be beta. You can do it for any prior density. So you start with any prior density, you can discretize it, and then you can approximate it by a discrete random variable. You can calculate the probabilities for each of those, and then you can generate a random sample. So one part of the problem, which is starting from a continuous density, how do we generate a random sample? I have shown you how to do. The other part of the problem, given a random sample, how do we know which density it came from? I haven't shown you how to do that. I just started to show that there is a match between the observed frequencies and the theoretical frequencies, and that's basically where we start. and from there we can develop an estimator from the orange line, which will give us an estimate of what the blue line should be. So that's how we go back, and of course our estimator will not be exact; it will be a approximation, and it will have its own error. All right, so that's all for this lecture for today. On Monday we will